Assalamu alaikum. Welcome to the next lecture on this Zbus building algorithm fault analysis. In this case, we'll actually use the Zbus to analyze the fault. So let us say we have a system which contains a number of buses as n. Let's say this is bus 1, this is bus 2, this is an arbitrary bus is r, and this is the last bus n. And we assume that at all these buses generators are connected. Like this is generator 1, this is generator 2, generator R in between 1 and n, and this is generator n. So assume a fault is occurring at bus R. The system then can be represented like this. So when the fault is happening at R, we can see that this is the fault current that is flowing from R to ground, and let's assume some fault impedance between the fault point and ground, which is represented by ZF. So we can convert this into it is Thevenin equivalent, where we know that we have to replace the point of fault and the ground by a voltage source whose polarity is given like this, and fault current flows from the fault point to ground. Polarity will be positive towards the ground side and negative towards the fault point side. So here, since we assume a ZF which is in series with the fault point in the ground, here also we use the same thing. So this is the Thevenin equivalent, and we have replaced all the generators only by their subtransient reactances or transient reactances. So this is the Thevenin equivalent of this circuit. So let us try to analyze this. Now this is V-bus, where V-bus fault will be this V-bus 0 should happen there. This so V1 0, V2 0 up to Vn 0. It's a column vector containing all the bus voltages. So V-bus F, that is the bus voltage of the fault at any bus, will be equal to V-bus naught plus some delta V, where delta V is the change occurring during the fault, due to fault. So this will be the bus voltage after the fault has taken place, because we know that this fault will definitely change the voltage magnitude, because any disturbance will change the voltage magnitude. Since we are talking about the fault, it will also change the voltage magnitude. Now this delta V will be equal to Z bus into delta I. So delta I have represented the IF, because when we do the fault analysis, we neglect all the load currents, because load currents are very smaller as compared to the fault currents. So I can represent it like this: delta V1, change in the voltage at bus 1, change in the voltage at bus 2, up to change in the voltage at bus 1, and this Z bus remains the same. This will be the change in the current in the bus 1. Let us say it is IF1, IF2, IFN. These are the fault current that may be injected into the bus, different buses, due to the fault current. We'll see whether it will be or it will not. And keep in mind, this is the injected current into the bus. So, but the fault is taking place at the bus R. That means IF1, that is the injected current at the bus 1. That is the current from, let's say, bus 1 to ground is 0, because there is no fault. Bus 2 is 0, bus N is 0, except at IFR, that will be equal to minus times IF. Why minus? Because the IF is directed from bus to the ground, and injected current is assumed to be that will be injected into the bus, that will be flowing into the bus. So that's why IFR will be equal to minus IF. So IF factor will be changed to this. All the elements of the IF factor will be 0 except that minus IF when IF is equal to R. So the voltages, this matrix can be then reduced: delta V1, delta V2, let us say delta up to delta VR. This is the voltage of the R bus at which this fault has taken place. This is delta VM. This is the same Z bus. I have only shown the row corresponding to the R bus. Otherwise, it is already over here also, but I haven't shown it here. I have shown it here because there is only one current which is corresponding to this bus, minus IF. Upon expanding this, first let us expand. Let us calculate delta VR from this matrix. So this delta VR will be equal to minus ZIR IF. because this delta VR should have been ZR1 into 0, ZR2 into 0, ZRR into minus IF, ZRN into 0. All the other elements will be 0. It will be reduced to delta VR will be equal to minus ZRR IF. Now, what is the value of delta V1? Delta V1 will be equal to Z11 into 0, Z12 into 0, Z1R into minus IF, Z1N into 0. There will be only one term that is corresponding to rth term, that will be Z1R into minus IF, that is this. Similarly, delta V2 will be equal to Z2R into minus IF, and delta Vn will be equal to Z minus ZNR into IF. In general, other bus voltages, that is all these voltages except VR, will be given as delta Vi will be equal to minus ZIR into IF. So this is the voltage change in voltage at other buses due to the fault current that is flowing in the rth bus. So VRF, that is the voltage at bus R after the fault, that is post fault voltage at the bus R, will be equal to VR naught plus delta VR. So VR naught will remain as it is, delta VR is this value, so it will be equal to minus ZRR into IF. So VRF is equal to this value. This is, let us say, equation 3. Also, you can see from this equivalent circuit, this VRF, that is the post fault voltage, VRF will be equal to IF into ZF. IF into ZF. VRF will also equal to IF into ZF. So equating these two equations, because this is also equal to VRF, this is also equal to VRF. So from here, that means IF ZF will be equal to VR naught minus IF ZRR. So IF will be equal to VR naught divided by ZF plus ZRR from this, because I will take it over here. It will be IF into ZF plus ZRR, that is VR naught. This is an important result. Fault current will be equal to the voltage at the bus divided by, okay, wait a minute. If ZF is equal to 0, IF will be equal to VR naught divided by ZRR. So this is the most case where ZF, you will see, will be equal to 0, and we'll be using this equation. So this is very simple. These equations you have used in your previous classes, that to calculate the short circuit current, and the short circuit current in the Norton case will be equal to the voltage at that node divided by the total impedance at the node. This is actually nothing but the impedance seen by the fault at this node or bus R, that is bus R and bus R and reference bus. So you can see it over here. This is the Thevenin circuit which we have already calculated. The total impedance seen by this, let us say only we have these 3 generators and we don't have any other, and the fault take place at the bus where these generators are connected. So the total impedance will be, that is seen by this point, and this point will be the parallel combination of these, this and this, if they are connected to the same bus. So this is the case when ZF is equal to 0. Now put the equation 5 into 2 and 3 we get. That means in this equation and in this equation. So first, let us say, try to, in this equation, that is minus ZIR into IF, where IF is equal to VR naught divided by this. So this is equal to minus ZIR into VR0 divided by ZF plus ZRR. So VIF will be equal to VI naught, because this VIF will be equal to VI naught plus delta VI, that is equal to minus ZIR divided by ZIF, that is this value, plus ZRR into VR naught. This is also an important result. This equation will help us finding the voltages of other buses where the fault has not taken place. Now VR is equal to VR naught, VRF is equal to VR naught minus ZRR IF. So it will be equal to, wait a moment, it will be equal to VR naught minus ZRR into IF is equal to VR naught divided by ZRR plus ZF. When we multiply, it will be ZRR plus ZF minus ZRR whole multiplied by VR0 divided by ZRR plus ZF. ZRR and ZRR will cancel out. It will be only ZF. So ZF divided by ZRR plus ZF into VR0. When VR is equal to 0, VR will be equal to 0 and ZF is equal to 0. That is for solid short circuit. This will be equal to 0. VR will also be equal to 0. And for this case, it will be equal to VI0 minus ZIR divided by ZF. Sorry, ZRR into VR0 if ZF is equal to 0. This is the voltage of the faulted bus. Now, post-fault current in the given line is given by IJF is equal to YIJ into YIF minus YJ. This we know earlier. It is nothing but the voltage difference divided by the impedance. Voltage difference of any bus. Let us say if we have to calculate here. If we have to calculate voltage current between these two, we can calculate the voltage between these two branches, that is V1 minus V2 divided by its impedance. So this impedance, when it is taken in the denominator, it comes out to be as admittance. So this is YIG, but this is not the element of the Y bus, because here it is simply, I should have written it as small YIJ. It is small YIJ into VIF minus VJF. That is the fault voltage of the ith bus and jth bus. It will be the current flowing from the ith bus and jth bus during the fault. Post-fault generator current, it will be equal to again the pre-fault generator current minus post-fault this terminal voltage divided by XGI. This also we know. This is very simple. Let us try to use all these equations and try to understand all this what we have done by using this simple numerical. So for the power system which was used in the previous example, that is this one. That is this one. Let us say a three-phase short circuit occurs at bus 3 and a solid one. The question is asking the same. Yes. A solid three-phase fault occurs at bus 3. Calculate the following. Fault current, post-fault voltage of the buses, current flowing after the fault through the line connected between bus 1 and bus 2. Let us see what happens. This is the Y bus, which we have already calculated, and this is the Z bus. So IF is equal to VR0 divided by ZRR, as I have told you earlier also. When the circuit and the voltages are not given, we can take the pre-fault voltage as 1 per unit. So I have taken it as 1 per unit, since this R, that is the faulted bus, is the third bus, so it will be equal to 1 divided by Z33, that is this much. So as I have told you, this is J, it is minus 1 divided by 0.175, and so 49 will be equal to minus J 5.71 per unit. So IF will be equal to this much. All the values are in per unit. So VR, that is the voltage at bus R where the fault has taken place. In this case, the third bus. It will be equal to ZF divided by ZRR plus ZR. Since it is a solid short circuit, there will be no ZF will be 0. So V3 will be equal to 0. So VIF is equal to VI0 minus ZIR divided by ZRR plus ZF into VRR. So here ZF is equal to 0. So for bus 1, V1F is equal to V10 minus Z13, that is I is equal to 1, R is equal to 3, ZRR is equal to Z33, that is 0.1749, that is this, Z13 is 0.125, so 1, pre-fault voltage 1 minus 0.125 divided by 0.1749, this comes out to be equal to 0.2583 per unit. That's the post-fault voltage at the bus 1. So for bus 2, when I is equal to 2, so I is equal to 2, so V20 minus V23 divided by V33 into V30 is equal to 1 minus 0.125, because V23 is also equal to 0.125. You can see to what V23 is this. So it comes out to be 0.125. V33 is same. This also comes out to be the same value. So V2F is also equal to 0.2853. So it has to be like this, because you can see, I will let you know what one thing, because when the fault occurs at this point and this point are symmetric with respect to this. Whatever happens to this, same will happen to this, because this is J0.25, this is J0.1, this is J0.1, this is J0.1, this is J0.25. You can see that a person at this point will see this and this in an identical way. So we can say the decrease in the fault voltage is also equal to same, you will see that the currents will also be same. So V2F is this. Now the current in line 1 and 2, I is equal to 1, J is equal to 2, that's I12F is equal to Y12 V1F minus V2F. Here it should have been small y12. So Y23 will be equal to 1 divided by J 0.1 because the impedance of line connected between bus 2 and 3 is 0.1. This one, J 0.1 to be precise. So it comes out to be into this V2F is 0.2853 minus 0 because V3F is 0. So it comes out to be J 0.2. Wait a minute. First we had to Y12. Y12 is a Y12 1 divided by J 0.1. No. Y1F and Y2F, sorry, V1F and V2F are same voltages, so the current flowing in the line from bus 1 to bus 2 will be 0. So this was actually asked in the question. Let us try to find out I23 and I13 also. That is Y23 V2F minus V3F. Y23 is also equal to J 0.1 into this 0.2853. It comes out to be equal to J 2.853. This will also be the same I13 because it is symmetric. The impedance between 2 and 3 and 1 and 3, you'll see they have the same symmetric nature. So the current from this and this will be same, and the total current will be equal to the fault current. That comes out to be 5.71. Okay, thank you. I will stop over here, and this is all about this subject.